All right, so this video is to work on this example on the mallard ducks and Canadian geese. We had actually done part of the mallard ducks in class, but I want to rewrite that on here because we'll need it for the comparisons to the geese. So when we were doing the mallard ducks, the things that we did in class together where we found the range, we said that the highest percentage for success was 85 minus the lowest, which was the 13. And that came out with a range difference of, that would be 72%. Then we did the mean for the mallard ducks. So we'll write that formula in here again as well. So we had that. We were adding all of the items from the ducks. So there were 5 different nest percentages that they came up with. So from those different areas, Montana, Illinois, Wyoming, Utah, and California. So those are the 5 locations they measured. So we had 56% of nests were successful, 85, and then 52%, 13, and then 39. And then we're dividing that by the number of nest locations that they essentially went to, which was the 5. And so that's going to be our X bar is going to be 49%. And again, we did this part in class. I'm just making sure we have all of this typed in so that we can compare them. So that's our mean for that one. Okay. And then this is where we were kind of ending up towards the end. We were doing the standard deviation using the sum of squares table to help us find that numerator part of our formula. So we had our 5 groups, which were our percentage groups that they had, which was 56, 85, 52, 13, and 39. Then remember, you do each item minus the mean. Our mean was that 49% up there. So 56 minus 49. We said that that equaled a 7. And then we had 85 minus the 49. And that one equaled 36. 52 minus 49, that was just 3. And then 13 minus 49, that was going to be negative because 13 is less than our mean. That was negative 36. And then we had 39 minus 49 equals negative 10. And we kind of talked about in class how if we tried to average this, just the differences, those deviations, it would equal 0. It's not going to help us because they're canceling each other out. I also did write in that the total we used when we found the mean was 245 for that. So that's how we got our 49% up here when we added that numerator. Okay, now we're squaring all these. So again, we did this in class. This was 49. 36 squared was 1,296. 3 squared is 9. Negative 36 squared is also positive 1,296 because you're squaring that negative as well. And then negative 10 squared is 100. We added all those together and that was 2,750. Now remember, that is not your variance or your standard deviation. That's just the numerator part of that formula. So when we look at actually finding the standard deviation and the variance, we need to know those formulas from our formula sheet. So when I look at the one for variance on the formula sheet, it's S squared equals the sum of squares, which is the sum of deviations squared over the n minus 1. It's always 1 less than the number of your sample when we're dealing with variance and standard deviation. If we had the population, we would have all of our n, but we have to adjust for the rounding errors. So this would be that 2,750 divided by, there were 5 nests that locations or states that we visited. So that would be 5 minus 1, which is 4. So just the variance ends up being 687.5. Now that's not the one that tells us how nicely spread out we are in percentages. We would need to get the standard deviation. So the only difference is you take the square root of that answer. So I just like to rewrite it in its fraction form and type this into my calculator because I'm less likely to get a rounding error than just if I've rounded this already. So this is approximately, and usually we round standard deviation to 2 decimal places. That's the typical. If they don't tell you, that's what I would go with. If they do give you rounding directions, obviously follow those. So that's 26.22%. So what that actually means is that, if our center is 49%, that's our mean. You could go 1 or 2 standard deviations, 3 standard deviations in either direction. Remember, if you are thinking about where is most of the data, it's usually within 1 standard deviation. So 49 minus 26.22%, and then 49 plus 26.22%. That would say most of the data would fall between the intervals we get when we do those subtractions and adding. Okay, so now we're going to switch gears and we're going to talk about the geese. So the range of the geese, we have to go back up and look at our data. The highest was 69 and the lowest was 18. So my range is going to be 69 minus 18, which is 51%. So a little less spread out. The ducks were a lot more spread out. It was 72% on the lowest to highest part, that range. Then we're going to do the mean. So we need to get our sum of all of our geese, which is 24 plus 53 plus 60 plus 69 plus 18. And we're dividing again by 5 locations that they source this from. This equals 224 over 5. So that's 44.8% if we do that on our calculator. Notice that's a little bit lower than the percentage we saw on the average for the ducks. So what that means, if you think about it, the average success rate, essentially. So the geese are actually less successful, have less successful percentages for their nest. All right, then we put our items because we're going to go work on getting that standard deviation eventually. So 24, 53, 60, 69, and 18. Those were those values. And then we're going to do the item minus the mean. So 24 minus 44.8. That's going to be negative 20.8. Then we have 53 minus the 44.8. That's going to be 8.2. 60 minus 44.8. Notice we always use the mean for that subtraction part. Is 15.2. 69 minus 44.8. That's going to be 24.2. And then 18 minus the 44.8 is going to be negative 26.8. And again, I could put my total here that we had for our, when we added all those together. All right, now we need to square each of these. So remember, you're going to be in your calculator. If you're squaring a negative, you should type it in a parentheses before you hit the squared button. So just as a reminder. So this is going to be 432.64. If I square 8.2, I'm going to get 67.24. You can double check these on your calculator. 15.2 squared is 231.04. 24.2 squared is 585.64. And then negative 26.8, again, making sure to put that in parentheses because it's negative, is 718.24. Now, if you add all of those squared deviations up, you're going to get 2034.8. Okay. So our variance, which is our S squared, is that sum of squares we just came up with. And we divide it by the number of items that we had minus 1. So remember, it's that n minus 1 down here. Well, we had 5 different locations that they got their percentages from. So 5 minus 1 is 4. Now, when I type this in on my calculator, I'm actually going to have to round it. It's 508.7 if we go to 1 decimal place. That is why I don't always type that value in, or actually that might be an exact value. Yeah, because it's divided by 4. Let's double check that, because if it's exact and not an approximate, technically you can type that in on your calculator. It was 508.7 and divided by 4. So no, oops, no, I typed in the wrong thing. Sorry. I typed in the answer divided by 4. It was 2034.8 divided by 4. There we go. That's 508.7 exactly. So it's not an approximate. So if it's not an approximate, you technically can get away with just putting the decimal answer under a square root and then taking the square root of that. But if it was rounded, if you did round this answer, you really would be better off by typing in the actual fraction under your square root. So I always usually just default to that, because unless there's rounding rules tell me to do like round at this step and then use that for the next part, I usually do this. And then we round standard deviation usually to 2 decimal places. So this is 22.55%. Once we take that, divide it, and then take the square root. Now, So let's talk about the difference. So we had the standard deviation being 26.22, so a little bit more spread out for the ducks. The ducks also had a mean of 49% success rate. So yes, there was more successful nest on average with the ducks, but with more variation. So it actually was a little more spread out. So most of the data is somewhere between, remember we said kind of 49 minus 26.22 to 49 plus 26.22. So we can kind of subtract and add and get those values, but you would see that's a little bit more spread out from its mean than this situation. The situation down here is that our average was 44.8, and we could, remember, subtract 22.55 from that, or we could add, and most of our data will be between those two new values. That's kind of called going one standard deviation on either side. And we'll have actual percentages of what that means later, but right now it's just kind of most of your data is between, like the bulk of your peak is going to be between those values. So a little less spread out, even though we had a lower chance of success. Okay, so that's what we can get from that. Now it says use the results from both the ducks and the geese to compute the coefficient of variation for successful mallard nest and Canadian, I should say Canadian geese nest. I don't know what Canada goose nest. Write a brief explanation of the meaning of these numbers. What do these results say about the nesting success rates for mallards compared to those of Canadian geese? Would you say one group of data is more or less consistent than the other, and explain? Okay, so we're going to write this out. We're going to do the one for the mallard duck. So when you're doing the coefficient of variation, you take your mean for, or excuse me, your standard deviation for that group, which this one was 26.22, and you divide it by the mean, which was 49. So this is for the ducks. And then we times that by 100%. So we divide and then times by 100. That ended up being about 53.5%. Okay. For the Canadian geese, that coefficient of variation would be that standard deviation, which was 22.55, divided by 44.8, and then times by 100%. This one comes out to about 50.3%. So what we can glean from this is that the coefficient of variation, oops, tells us a ratio of standard deviation, I'm just abbreviating some stuff, to mean as a percentage. The CV for mallard's nest is slightly higher. Sorry, this keeps trying to form boxes, so it's trying to do text boxes. This means that the nesting success rates for mallards is more variable or spread out greater than for geese. Okay. And then the geese have a smaller CV, which also indicates they're more consistent. So the geese having the smaller CV makes them more consistent. What that just means is more consistent means more data points close to your center. Okay. All right. Now, the last thing we need to do for the geese problem and the duck problem is find the 75% Chebyshev's interval around the sample mean for both the ducks and the geese. So remember, we learned 3%. It was just like 75. Let's go back up to the rule. 88.9 and 93.8. They're such weird decimals that I have to look them up too. But the 75 means you take your mean and you subtract the standard deviation twice, because they're using population symbols for that. And then we take the mean and we add the standard deviation twice. So that's what we need to do to find those intervals for both of those. So I'm going to write that in formula form here. So for the mallard ducks, we would have to do 49 was the average for the mallards. We would subtract 2 standard deviations. So times this by 2, and then we'll subtract. And we'd take the mean, which was 49%, and we'd add 2 of the standard deviations. So this would mean that at least 75% of the data falls between these values. Actually, this one comes out negative. This is more than that. So when we subtract it, we get negative 3.44%. 2, and this one ends up being more than 100%. So actually, 100% of our data falls in this, but Chebyshev's theorem just says at least 75%. That's his guarantee, because he's not sure if our data is symmetric, skewed, so he lets his percentages account for many variations of that. So I 100% agree, at least 75% of our data was between those two percentages. They were all in between there. And then for the Canadian geese, we have their average was 44.8 minus 2 standard deviations, and 44.8 plus 2 standard deviations. So this one would be that at least 75% of our data falls between negative 0.39% to 89.9%. And that I got those values from doing those 2 math formulas for that specific row. So just be aware, sometimes it'll be more than 75%. At least means 75% or more. So it's not like it cuts it off there. So yeah, so this, if you look up here, I believe that also included all, yeah, nothing was bigger than in the 80s at all. So both of our groups, this formula says Chebyshev's theorem accounts for that, essentially. At least 75% of the data will be between those units of measurement. Now, that means our data probably wasn't very super skewed, because that's when you get values that might fall outside of the ranges that you get. It would be if your data set had a lot of very weird outliers that are far, far away. So there is actually still one more problem on this specific section on standard deviation, but it is a tricky one. So I want to do that together in class. So we'll have that one left to do on Wednesday. The U-tries will be in the notes I already posted, so you can check the ink out on those. And then we'll be moving into the box and whisker plots. All right, I hope you have a good day.